Hello, this is Dr. DA, and this is the third video. In this one, I'm going to walk you through a set of calculations for experiment 5, molar volume of a gas. If you remember, we are studying the reaction where potassium chlorate decomposes into KCl and oxygen gas. Now, what we're doing here is we are not doing this reaction with pure potassium chlorate, but with a mixture of unknown composition. The reason is that in that mixture, we also have this other compound, manganese dioxide, which, as we explained in the intro, behaves as a catalyst. It helps the reaction move along. So one of our first objectives in this experiment, remember, is to find out, well, what is the percent composition of potassium chlorate in that mixture of unknown composition. The second thing we're doing is we're going to take our gas product here and we're going to determine experimentally several things: the number of moles, the pressure, the volume, and the temperature. But we're going to do this under our lab conditions. And then we're going to use the combined gas law to find what is the volume of this gas. I'm sorry, I lost my place here. Okay, here we go. Let me get this out of the way. We're going to use the combined gas law to find the volume of oxygen at STP, standard temperature and pressure, which for us, we're going to represent as 0 degrees Celsius and 1 atmosphere of pressure. So that's what we're going to be calling STP, standard temperature and pressure. Okay? So if you remember, the way we conducted the experiment was we set up this apparatus that I showed you in the previous video how to do it. Our potassium chlorate is going to be heated, and as it heats, it produces oxygen gas. Oops, I'm sorry, I got some weird stuff here. Produces oxygen gas, which then emerges into this reservoir here, where it causes water to get displaced through this delivery tube, and it then emerges into this beaker where we're going to collect it, right? After we have finished the reaction, we said that we typically have the water in the beaker and the water in the flask at different pressures. So the thing that we did was we equalized the water levels here, right? Because when we do that, the pressure inside our flask will equal the pressure on the outside. And that is the pressure that we are going to be able to measure. This will be the pressure of the air. The other thing we said we would do is we would measure the volume of displaced water here. And we're saying that however much water was displaced, that space is now occupied by the oxygen. So this will be equivalent to the volume of oxygen. We also measure the temperature of the water in the flask, and because of rapid energy exchange, that should be equal to the temperature of the oxygen. A couple of things. One of them is what we really need is the pressure of the oxygen alone, and as we're going to see in our calculations, that's going to require that we make some adjustments. So we'll have to adjust this to find the actual pressure of the oxygen. Also, the question came up in our demo: how do we find out the number of moles of oxygen gas? Well, for that, we are going to rely on the stoichiometry of the reaction. Okay? So we are set up. So what I'm going to do next is I'm going to show you a sample set of data by a former student of mine, and this was Susan. She had a younger brother, Johnny, who was my student later on, and very smart young woman. She had this kind of interesting quality. Every now and then, you would look where she was, kind of like she wasn't there anymore, like she was almost invisible. And then you look again, and there she was. So anyway, that was one of my former students, and as you can see here, she collected data similar to yours. I hope you remember to write down what your unknown number was, or alternatively, perhaps your instructor did not give you the unknown number, but they recorded it on their roster. So either way, the idea is your final result should match close to what the real values should be for that unknown. Okay? One of the things that I do here is, before I do my calculations, is I like to put numbers on these items. So I'm going to put numbers here. That'll be number 1, 2, 3, 4, 5, 6, 7, 8. Notice that Susan had here the mass of the empty test tube, and then the mass of the test tube plus her sample. And then after the first cycle of heating, she had the mass of the test tube plus her product. And then she had the same result, the same entry here after the second round of heating. Because those were, and I'll show you later, within the limits that we established for heating to constant mass, she was not required to do a third round of heating here. Again, the pressure, let me remind you of how we measure the pressure in this experiment. Let me see if I can find my barometer here. Here it is. Okay, so this is our barometer. And as I explained earlier, the outside scale of the barometer is given in centimeters of mercury. Oops, let me get that out of the way. This is in centimeters of mercury. And so we had to convert it to millimeters, which is torr. You can see we're between 76 and 77, for example. There are 10 intervals. So that means that the scale is calibrated to 1/10 of a centimeter. And because it is a graduate scale, as we were instructed, we have to add one more decimal. So right now the needle is right sitting on the 76.3 interval. So we're going to say that, let me put this a little bit smaller here. Okay, and let's say this is our reading here. Oops, sorry, I got some kind of weird things coming up here. All right, so here is our reading here. So we would say that that was 76.3 centimeters, but we have to add one more decimal, so that'd be 76.30 centimeters, which means that when we convert that into millimeters, that would be 763.0 millimeters. So you should have recorded your pressures to 1 decimal of a millimeter. Okay? So let's come back here to our sample data sheet. We're back in here. And so what I'm going to do now is I'm going to walk us through some calculations. All right? I'll display some of them, but not all of them. I want to put these on a separate piece of paper. This is going to be my calculations worksheet. And remember that the idea here is that if somebody from the outside comes in, you want them to be able to follow along what you did. So this should not be just like chicken scratch, right? It should be fairly well organized. So I'm going to put here my, I'm going to put here my calculations. And I'm only required to show the calculations for one trial. So I'm going to show here, I don't know why this is happening here, for trial number 1. Of course, you'll have to do calculations for both trials, but you're only required to display one set. The first one I'm going to do here is I'm going to make sure that we did heat to constant mass. So I'm going to put here heat to constant mass. All right. And to do that, I'm going to compare the values she had here in item number 4 and item number 3. These are the 2 rounds of heating, right? So item number 4 minus item number 3. So those numbers that she had here were 23 point, I don't know why it's doing this. Kind of weird. 23.5736 minus 23 point, 23.573, and I don't know why this is doing this, but hey, this should be equal, oops, this should be equal to 0.0004 grams, which is the same as, zero point 0.4 milligrams. And so therefore we were safe in not having to do a, like we said here, a third run of the heating cycle. All right. So my next goal is to start calculating these things here. So what I'm going to do is I'm going to put numbers here on these items. So I'm going to call this number 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21. Now here's what I would do if I were you. At this point, you will have received a sample set of data with a Mach unknown. If I were you, what I would do is I would go through these calculations with your numbers and follow along as I do mine. Of course, you can always simply follow mine with these numbers that are here from my student Susan's, and then you can go back and do your calculations. Please await instructions as to how we're going to require you to upload your lab report in the end. So for the moment, just follow along, perhaps with your own calculations. Okay, so the first thing I want to find out is what was the mass of my sample. So that would be essentially the difference between the full test tube and the empty test tube, which is items 2 and 1. Okay, so I'm going to come back here to my calculations page, and this is going to be item number 9. And this will be the mass of my sample. And again, this will be item number 2 minus item number 1, which in this case is 24.0792 minus 21.8372. And careful with sig figs. This should be a total of, 2.2420 grams. Okay, that's the number that I'm going to put in here. All right, erase that. Let me see if zooming this up will help me out here. Zoom in a little bit here. Okay, so I'm going to put in here 2 point, wow, 2 point, 2 point, $24. Okay, 2420. Gosh. Okay, I'm having some problems here with this technology. Please forgive me, but I'm going to keep on trying, and hopefully you can follow along, okay? I'm going to see if I can fix this guy here. Okay, wow. 4, goodness. Okay, I can do this. 2420. Yeah, it seems like the tip of this electronic pen, this stylus, is kind of like acting up. And it's giving me a lot of kind of weird stuff here. I don't know why, but I'm going to keep on trying because we got to use up our time. Okay, the next thing is to calculate the mass of the oxygen. Now remember, when we look at the chemical reaction that we're working with here, right? We said that basically whatever initial mass of potassium chlorate I had in here has now been converted into a mass of KCl and a mass of oxygen. The oxygen has escaped my test tube, so all I have left is the KCl. That means that whatever difference there is in mass between the product and the initial, that should have been equivalent to the mass of oxygen that escaped. So, coming back here to our data, oops, sorry, that's not it. Let me go back here. Coming back here to our data from Susan's thing, we can see that the difference between the mass of the test tube plus product and whatever mass you started with, right? That'll give you the total mass of oxygen, right? So what we're going to do is we're going to take your initial mass. I'm sorry, I probably said that in reverse. We're going to take the mass of test tube plus sample that we started with, and we're going to subtract the mass of the test tube plus the product. I'm going to use the final number here. So going back to my calculations here, okay, I'm going to work now on item number 10, which is the mass of oxygen. And like we said, that should be the difference between, in this case, the starting mass and the final mass, okay? So that should be, in our numbers here from Susan's, that would be 24.0792 minus 23.5732, and that equals 0.5060. All right? So that's going to be the number of grams of oxygen that we have. And I'm going to come back here, and let me get this out of here and come back in here, and we're going to write down this 5060 grams. Since the units are already indicated here on the left side, I don't need to repeat them in my data here, okay? So that's my mass of oxygen. Okay, now comes the interesting part, which will take care of the first item in our goals, in our objectives, all right? So let me come back here to our calculations. What we're going to do now is we are going to try to calculate what is the mass of potassium chlorate in my initial sample. So to do that, let's remember what the equation was, right? So this is item number 11. So our equation was 2KClO3 reacting to form 2KCl plus 3 units of oxygen gas. Now, this tells me that for every 2 moles of potassium chlorate that decompose, 3 moles of gas are produced. So I'm going to use that ratio, but again, like in stoichiometry, we have to do this transaction in moles, but the units that we've been given are in units of grams, so we had to do the conversion. So starting with 0.5060 grams of oxygen, we had to convert that into moles. So 1 mole of oxygen is, remember this is O2, so that's 32, not 16 grams of O2. According to the equation, 2 moles of KClO3 are decomposed to produce 3 moles of O2. We can cancel those out. And if you had time, you can calculate what is the molar mass of KClO3. I'm not going to show it here. You are able to do that. It's 122.55 grams, all right, of KClO3 for every mole of KClO3. All right, so that's where we're at right now. And you plug in those numbers in the calculator, The moles of KClO3 are going to cancel out, and this gives me a total of 1.292. Remember that because in here the initial mass of oxygen only has 4 sig figs, we can only round this to 4 sig figs, so the grams of KClO3. So let's take that number and bring it back here to the data sheet. And over here, I'm going to put in 1.29, oops, kind of acting up again. Okay, 1.2, wow. Okay, let me see if I can make this happen here. 292 grams of potassium chlorate. Remember, our first objective in the experiment, right, was to find out what was the percent of potassium chlorate in our mixture. So now that we have the grams of potassium chlorate, we can come here and calculate what is the percent potassium chlorate in our mixture. So this will be item number 12, percent of KClO3. So that's going to be, we have 1.292 grams of KClO3. And our initial sample we said was 2.2420 grams of sample times 100%. And we can calculate that. Again, it'll be limited to 4 sig figs, and that comes up to be 57.62%. And that is what we're going to write down here in the percent KClO3, 57.62%. Of course, when you do your second trial, you'll have a second value for the percent of chlorate, and so you'll have to calculate the average and put it in here, okay? I don't have Susan's second trial data here, so I can't do that for you, but you should be able to simply calculate the average of those two, okay? Okay, hopefully, let me give you a few moments to process that. And what I'm going to do now is I'm going to go to a second calculations page, and I'm going to continue doing calculations here, and we're going to tackle now the second part of our goals, the second objective, which was to calculate the molar mass of a gas at STP. So calculations, and this is continued. So I'm going to start here with this item that we had here, which was the mass of oxygen. And number 14, we already have that, right? We had already calculated that. So I'm just going to write in here what we calculated earlier in item number 10. So this would be 0.5, oops, 0, oops. Just don't know why this stylus is doing this. 60. All right, kind of a choppy approach here. Sorry guys, I'm new at this, so please forgive me. And what I want to find out now is the number of moles of oxygen. So I'm going to jump back down here to my calculations. Item number 15 is going to be the number of moles of oxygen. So we have essentially 0.5060 grams of O2, and we already saw that 1 mole of O2 will be 36.00 grams. Okay, so that'll give us the number of moles of oxygen here. Of course, we're limited to 4 sig figs, so this will be 0.01521 moles of oxygen. That is the amount of oxygen produced. Now, of course, if you had been a little more thinking ahead of time, you probably could have gone here when you did this calculation and saved this in your calculator, because that's exactly the calculation we just did, and then you would have it there. Dr. D.A. Did not have that gift, so I had to do it again. Okay, so we have here essentially 0.01521 moles of oxygen. I'll tell you what, let me fix this a little bit here. Make it look like a 1 and not like Okay, I can do this. This is going to be, oops, A1. Okay, A1 in there. Okay, there we go. Sorry for my shaky hand. Okay, so now comes the calculation of the volume of oxygen. Now remember, we're trying to find out what is the volume of 1 mole of gas under our conditions. Okay, so I'm going to come back here. We have right now, we are saying that the volume of water displaced equals the volume of oxygen that we collected. We're also saying that this is the number of moles of oxygen we collected. So between items 15 and item 8, we can calculate that. So I'm going to come back here to our calculations, and we're going to work now on item number 16. And for item number 16, we're going to calculate the molar volume of oxygen. We write it this way with a bar here. So that's going to be essentially the let me work that up. All right, it's going to be 392 milliliters that we collected, but we want to change that into liters. So remember that it's 10 to the negative 3 liters per 1 milliliter divided by the number of moles, 0.01521 moles. So the idea here is the milliliters cancel out, and this is going to give me a result that is going to represent the number of liters per mole. So when I do that, I'm going to get a total of 24.8 liters per mole. Notice that, again, we're limited in terms of sig figs here. So that's the number we're going to put back into our data sheet. So back here, we're going to put 24.8 liters per mole. Now this is under our lab conditions. Our goal is to find out what would be the volume of a mole of gas at STP, standard temperature and pressure. To do that, we had to use the combined gas law. But before we get there, we had to now do some adjustments here, okay? So let's go ahead and do some of those adjustments. Notice that we're going to be finding out what is the pressure of the water vapor, and you're going to have to find that out in your table. That's in the second page of your lab manuals, the procedures. And then we're going to calculate what is the pressure of the dry oxygen. So let me go here over to item number 17. And Susan's data is going to be interesting. We're going to have to get this from the table. And this table, I believe, is on, That table is going to be, I believe, either on page, on page 14, of your lab manual. The problem is that over there, what they show you is they show you the difference, the vapor pressure of water at different temperatures. I'm sorry, I don't have that picture here with me, so please look it up. And what happens is that, it turns out that, as you can see, Susan's temperature was actually 24.5. If we look at the data in that table, they give me the vapor pressures at 23, 24, 25, in other words, in 1 degree increments. So I'm going to assume that between 24 and 25 degrees, the increase in vapor pressure is fairly linear. So for 24.5 degrees Celsius, I'm going to say that it's between 24 and 25 degrees Celsius. How about that? And I'm going to have to look up those numbers. If you look at that table, 24 is 22.4 25 is 23.8. So I'm going to take the half point of those, and this is going to come up to be 23.1 torr. Okay, and that is the number that I'm going to put back here, 23.1 torr. Okay. Okay, now I'm going to come back to my calculations, and I'm going to find out now what is the pressure of the oxygen. So remember that in the flask, the pressure inside the flask was equal to the pressure on the outside. But inside the flask, what we had oxygen, and we also had water vapor, because anytime that you give a liquid space above its surface, some of its molecules are going to vaporize. And we'll study that phenomenon later in the semester. So we said the pressure on the outside is the pressure of the air. So if I want to find out what is the partial pressure of oxygen, I need to subtract the pressure of the air minus the pressure of the vapor of water. And in our hands, this was the pressure of the air. We said was from item number, this was item number 6. And the pressure of water we just calculated here was item number 17. All right. So that is 758.5 minus 23.1. And that comes up to be 735.4 torr. Okay. So that's the number. I'm going to come back up here to our data sheet, and I'm going to write this number down here. So this is 735.4. Oops. So this 735.4. Okay. So that is the pressure of the dry air. Now our next calculation involves changing the temperature into Kelvin, because when we use the gas laws, we have to go to Kelvin, all right? So the temperature was 24.5 degrees Celsius. So I'm going to have to convert that into units of Kelvin. And what I'm going to do is I'm going to come back here, and what I'm going to do is I'm going to add another page here. And so we can go here, and we're going to continue our calculations here on this page. So this is calculations. Oops. Every time I write this, calculations, continued. Okay, having problems with this guy again. Okay, so this is, let me try this again. Oh my goodness. I do not understand why this is happening. Now, those of you who are iPad savvy, you probably are laughing at me right now and saying, I know exactly what you're doing wrong, Dr. DA. Unfortunately, I had an assistant here who's not here right now, so I'm going to keep on trying. Goodness. Okay, I got to write continuation there. Let's see if I can close that parenthesis somehow. Okay, here we go. All right. So what I'm going to do now is I'm going to calculate the temperature in Kelvin. This is item number 19. Okay. Sorry, number 19. And this will be the temperature of the oxygen in Kelvin. So our measured temperature was 24.5. 0.5, and to get Kelvin we have to go and add 273.15. Oh my goodness, I'm sorry guys, I just don't know how to use this. 273.15, and that's going to give us a value that has to be rounded to only one decimal, because that's what this was, and that number will be 297.7. This is so shaky. I'm sorry guys, I apologize for the technical glitches here. So I'm going to come back here and write this down. 297.7. I think by now you guys are getting frustrated with me. So just please bear with me. We only have like a couple more things to do. So please bear with me. I'm very sorry that I cannot get this to work the way I want it to work. I apologize for that. But here we go. I'm going to try to find out if I can make this work now to calculate what is the volume of 1 mole of gas at STP. Remember, right now we came up with a value, but this was under our lab conditions, right? Which were, 758.5 total pressure, 24.5 degrees Celsius, right? So I want to change that. So what I'm going to do here for this item is I am going to try to use the combined gas law, which is P1 times V1 okay, still having problems here, over T1 equals P2 times V2 over T2. Now what are these? This first set of values represents the conditions that we did the experiment in our lab. The second set of conditions represents conditions at STP. We are going to be talking about the volume of 1 mole, so I'm going to go ahead and put a little bar here on top of these guys to represent that. And now we have to say, well, here's the thing. We are going to try to calculate this at STP, but what our unknown is the volume of a mole of gas at STP. So what we're going to do first of all is let's clear this out here. Let me first see if I can get some of this stuff out of the way here. I have a lot of ink blots in here. Okay, I'm going to come back here to the smaller eraser, and then I'm going to come back here my pencil. So I'm going to first of all go ahead and clear this out, rearrange this equation so I can solve for the molar volume of V2. So that would be P1 times V1 times T2 divided by T1 times P2. Okay, so those are the numbers I'm going to put in here. So let me put in those numbers, and then we're going to do the calculation together. All right, here we go. So we said that the pressure for our gas in our lab conditions was 735.4 torr. And then we said that our volume of a mole of gas was 24.8. Goodness. 0.8. And this is liters per mole. And then our temperature at STP is 0 Celsius, which is 273.15 Kelvin. All of that divided by T1, which is the temperature at which we did our measurements. So that would be 297.7 Kelvin. And then the pressure 2 would be the pressure at STP, which is 1 atmosphere. But we're going to use torr for this. Okay. Notice that if we carry this out properly, the units of pressure cancel out, the units of temperature cancel out, and we're going to be left with units of liters per mole. So what I'm going to do here is, to help us out a little bit, is I'm going to bring out the calculator because I don't have the calculations for this. So let's see if we can do this for a moment here. And maybe in your iPhone this looks a little kind of like crunched up, but just bear with me. So let's put these numbers in here, okay? Let's see. So we have, oops, what is this? This calculator is showing me like a, what it's showing me is a, it's not showing me calculator, it's showing me alphabetical stuff. Okay, here we go, found it. Okay, so we're gonna put these numbers in. 735.4 times 24.8 times 273.15. We're going to divide that by the temperature, 297.7, and divide that by 760. And that's going to give us 22.0183159. Okay, coming back here, I'm going to write that down. 22.0183159. Obviously, we only had, let me get the calculator out of the way here. Okay. Obviously, we only had a value here that was good to 3 sig figs for the molar volume. So we had to round this to essentially that. So that means that we're going to be rounding this to 22.0 liters per mole. Okay? And that's the number we're going to put up here. And back to our data sheet. We're going to write here 22.0 liters per mole. Okay, now remember, last but not least, our goal was to find out how close did we get to the actual reported value. So we're going to calculate the percent error now. So let's go back to our calculations. And we know that the actual value here is supposed to be 22.414 liters per mole. That is the value that was determined scientifically and was applied to find out what the value of the gas constant was. So let's go ahead and calculate our percent error. Remember, percent error is the absolute value of the difference between our value and the real value. So 22.0 minus 22.414 divided by the real value, 22.414 times 100%. Okay? When you do that calculation, you'll realize this difference here is essentially only valid to 1 decimal. So it's going to be something like 0.2 something. So actually, let's go ahead and do that calculation here. Let me bring the calculator again. Okay, let's clear this out. And now I'm going to show it to you. So 22 minus 22.414 equals that. We're going to take the actual positive of that. I'm trying to find out how to change signs here. Where's the change of signs? Can't find it. Anyway, so we'll just keep it there. Oh, let's just do that then. Okay. Oops. Let me do that again. Okay. 0.414. Okay. Okay, so that's the absolute 0.0414. Oh, that's not it. Okay, it's 0.414. Here, let me just clear this out, 0.414. We're going to divide that by the total value, the real value, which is 22.414. Now, remember that when we did the subtraction, the value that we put in, 22.0, only had one decimal. That means that we can only use one decimal of this top part here. So when we do this, right, and we multiply times 100%, we're going to get 1.847 whatever, but we can only round that to 1 sig fig. So that means that we had to round that to 2, and therefore that's going to bring us over here and make this essentially 2%. Okay, let me get this guy out of here, move it out, and we're going to come back here to our data sheet, and we're going to input the 2% error. And of course, what will happen now is Susan would have done a second trial. I don't know, it seems to have disappeared. I couldn't find it, but you will have a second trial. And what we will do is when we get your lab report, we will look at your results. First of all, we're going to look at, how close did your average percent composition came to what it should be. And also we'll look at these values here and compare how do they compare to each other and how do they compare to the real value in the literature. Okay? Don't forget that there may be some post-lab questions that your instructor is going to tell you to do. So please listen to your instructor or read their memos. All right? Thank you so much for being such good sports. Again, I apologize for my poor handling of this technology, but hopefully this was good enough for you guys to be able to use your data and do your calculations. Thank you so much. We'll talk to you soon.